Hey guys, so for this video, why don't we go over resonance, right? Chapter 8. Resonance is when you have two different structures and they differ only by electron arrangement, not by number of electrons and not by the skeleton. So let's get a couple examples of this. So we're going to have to go through all 5 steps to do this. We're going to have to draw the Lewis structure of nitrate, right? So nitrogen has 5 electrons. How do we know that? 1, 2, 3, 4, 5, and it looks like oxygen has 6. So it's 5 plus 3 times 6. And then we have a negative sign here. Does that mean we have 1 extra electron or we're missing 1? It means we have an extra electron. So it's really 18 plus 6, we're talking 24, right? So I need 24 electrons in this structure. Nitrogen is going to be in the center. Let's draw our skeleton, shall we? All right. So, and then we can't ever forget to have our negative sign out there, right? Because we have to account for the fact that it is an ion. So far we have 6 electrons in this structure drawn. We have 3 single bonds, so 6 electrons. So what's our next step? So we drew our skeleton, so now we complete the valence electrons on all of our surrounding atoms, right? All right, so we have now 24 electrons. Hey Carla, I'm done, right? I'm done, I don't need to do any more, right? But that's not true. If you were to check the formal charges, the formal charge of oxygen would be 6 minus 1/2 of 2 minus 6. This would be a -1, -1, -1. And if we calculated it for nitrogen, we would have 5, because it has 5 valence electrons, minus 1/2 of 6, so it'd be 5 minus 3, it'd be plus 2. Now, remember, formal charge, we want to keep it as low as possible. So if you're playing at home, you can pause it and go ahead and make sure you can calculate out those resonance charges. How do we know nitrogen isn't satisfied? Because nitrogen does not have an octet. So what can we do? We can't add or take away any more electrons. We can't do that. But what we can do is zhuzh them around, right? So let's take the electrons from right here and let's actually just make a double bond there. So now if we were to check it out, oxygen has 6 valence electrons, so 6 minus 1/2 of 4, so 6 minus 2 minus 1, 2, 3, 4. This is now 0. This is still -1, -1. Nitrogen is now +1. So this is the most correct structure that we could have. All right, so let's talk about why this oxygen was so special, that it was the one that got to double bond. It's not, actually, right? On an atomic level, they're all very equal. So what you do is you represent them with double-headed arrows. And why don't we show the exact same structure, but with this oxygen double bonding? So these are resonance structures. Like I said earlier, they differ only in electron arrangement. The skeleton is still very much the exact same. So they only differ in electron arrangement. Well, hey, don't you see another possible resonance structure? I do. We could have this one be the double bond. So let's show that. Double-headed arrow. And then this nitrogen, this one's the double bonded oxygen. Okay. So this is how you draw the resonance structure for nitrate. And we double checked with formal charges, so this is the most correct. So the thing is that does this electron exist here, or here, or here at any given time? The thing is electrons move so fast that technically it exists in all three places at the same time. It's sort of like if it were to jump from here to here to here, and it did it so fast that it kind of became a blur, right? So there's actually one bond between each of these oxygens and the nitrogen, but there's also a third of a bond, because a third of this extra pair is here. So it's 1 1/3 bond each. Resonance, keep in mind how fast these electrons move. They don't, if we were to take pictures of this, we wouldn't be getting a picture of this, this, or this. We would be getting a picture of this with the second bond blurred equally between all three spots. All right, so let's talk about a different situation where we can represent SCN, right? Let's represent this in a way where we're going to see if there's a difference. So actually, this one will not work out so well. Let's do SCN plus. Why don't we do that? Okay, I'm trying to find one that mimics the quiz, right? So we're going to have an S, a C, and an N. That is going to be our skeleton. Let me double check that this is the example I want. Yeah, SCN minus. My bad. SCN minus. Let's do that one. Okay, so let's do SCN minus. I don't know why I was hung up on that. All right, let's check out what possible resonance structures there could be. So if I were to complete this, I need to do my first step, which is total it out. So sulfur has, it looks like 6 electrons. Carbon always has 4. Nitrogen has 5. And then since it's a negative sign, we're going to have one additional electron. So it looks like it's 6 plus 6, so 12 plus 4. So it looks like we're talking about 18, right? Okay. No, we're talking about 16. Oh, 12 plus 4 is 16. I can do math, but, you know, staying at home. 12 plus 4 is 16. Very good. Okay. So let's do what we would normally do and complete the octets on the outside. So 1, 2, 3, 4, 5, 6. Now there are 8 electrons around sulfur. 1, 2, 3, 4, 5, 6. Now there are 6 electrons around nitrogen, but carbon is not satisfied, so this is probably not going to be a good example. So I could have a situation where I have sulfur double bound to carbon, and why don't we make nitrogen double bound to carbon as well? Satisfy carbon's octet. So in this situation, we still have 16 electrons, right? 8 around each of these guys. But let's check out the formal charges while we're at it. So the formal charge of carbon is going to be 0 because carbon has a valence electrons number of 4 minus 1/2 of 8. So 0. Let's check out nitrogen. Actually, you guys let's draw all the possibilities, shall we? How about, what if sulfur were to be the one to triple bond to carbon? Isn't that a possibility? Instead of sulfur just donating 1 pair and nitrogen donating 1 pair, what if sulfur donated 2 pairs in between them? So this is a possibility. What's another possibility? Running out of room, but that's all right. What if nitrogen was the one to triple bond? So we have these situations where nitrogen could have been the one to triple bond. So these are technically resonance structures, aren't they? Because the only thing that differs between them is the location of the electrons, not the number of electrons and not the skeleton or arrangement of the molecule. So, carbon in all of these situations has a formal charge of 0 in all the situations because it's bound 4 times. What really is interesting is the formal charge of sulfurs and nitrogens. So let's figure those out. Looks like sulfur has a valence of 6, right? Sulfur has a valence of 6 electrons. So it's going to be 6 minus 1/2 of, and how many bonded are around sulfur? There are 4. So 1/2 of 4 minus, and how many lone electrons are on sulfur? 4. So it's 6 minus 2 minus 4. So we have a 0 on this sulfur. And if we remember from back in the day, 0 is good. 0 good. Nitrogen here comes with 5. This is just my scratch work, right? Nitrogen has 5, if we look at the periodic table, minus 1/2 of the bonded. How many bonded around nitrogen right now? Looks like there are 2, 4, so there's 4. And how many lone electrons are on nitrogen? 1, 2, 3, 4, so minus 4. So it looks like for nitrogen here, it's going to be 5 minus 2 minus 4, so minus 1 for nitrogen. If we go back and remember from my formal charge little lecture, you'll see that the formal charges of the atoms have to total up to the net charge of the atom. And in this case, 0 plus 0 plus negative 1. Good, totals out to negative 1. So we're going to go fast through here. Sulfur has 6, so 6 minus 3 minus 2, so 6 minus 3 minus 2. Oh man, what? Oh, brain. 6 minus 3 minus 2, it's going to be a plus 1. Right? Nitrogen is 5, so 5 minus 1, because it's 1/2 of 2, so 5 minus 1 minus 1, 2, 3, 4, 5, 6. 5 minus 1 minus 6, so we're at minus 2 here. So already, which structure looks better between these two? This structure looks better because we're dealing with smaller formal charges rather than a whole positive 1 and a negative 2. We'll keep going. This structure here, sulfur comes with 6, correct? So 6 minus 1/2 of 2, so 6 minus 1 minus 6. So we're going to have a minus 1 on this one. And nitrogen here, right? 5 minus 3 minus 2. Nitrogen's going to be 0 in this case. So it looks like our two contenders are these. This one is probably not the best structure, right? Because it has such wacky formal charges. The only difference between these two, this is tied very closely to your quiz, is the placement of the negative. So what we have to ask ourselves is the negative more comfortable on the sulfur or on the nitrogen? So what we're going to have to do is look up the electronegativity. And I do not have that pulled up, so let's get that out. The electronegativity of the atoms. So the negative 1 is going to rather stay, so this is slide 5. The electronegativity of sulfur is 2.5. So sulfur's electronegativity, 2.5, and it looks like nitrogen's electronegativity is 3.0. All right, so that is the difference between sulfur and nitrogen. So the negative charge would rather exist on the nitrogen or on the sulfur? The negative charge would rather exist on the most electronegative atom. So it would rather be here. So it's where sulfur is double bound to carbon, and nitrogen is the one that has this negative charge. Everything else is neutral. Over here, is this structure okay? Yeah, it's all right, but is it the most stable? No. The negative charge would most prefer to be on the most electronegative element, and in this situation, it's not. So that's tied to your quiz very closely. All right, so that's it for resonance. Thanks, guys.